Good afternoon, everybody. On behalf of the organizing committee for the Lignin Biobased Materials, I am very pleased to welcome you into this 4-day event that will take place starting today and finishing on Thursday. Every day will be starting at 1:30 p.m. Costa Rican time, and we will have a series of talks from researchers in Brazil, Costa Rica, and also in Canada. We are very pleased to have this event, which it started from a collaboration that we established between the Costa Rican American Chemical Society student chapter at the Universidad Nacional, where I am the faculty advisor, and the ACS professional chapter at Universidad Estadual Paulista with Professor Leonardo Fernandez Fracheto. We're very pleased with this collaboration that eventually involved Dr. Ana Francis Carballo, Dr. Oscar Rojas, and it eventually evolved into this event that we're having today. And for that, on behalf of the Biomaterials Research Network, the Office of the Research Vice President of the university, and everybody at the School of Chemistry in Universidad Nacional in Costa Rica. I welcome you once again, and I thank you for your participation. So in order to start this event, I'm gonna yield to Dr. Ana Francis Carballo.
Thank you, Jose. Welcome everybody to our first talk of the week. As Dr. Rodrigues mentioned, we will have different talks along the week. So please feel free to join us the rest of the week. We even have on Thursday afternoon, we have a workshop, which is going to be given virtually as well. So you can see the results of the learning the student had as part of the exchange activity she did at the university in Brazil. So I have to present today Jessica. This is my first time seeing her. We have been writing each other emails, and so thank you very much for accepting your participation in this activity. So Jessica Rodrigues has a bachelor's degree in chemical engineering from the University of Sorocaba in 2016. She also has a master's degree in 2019 and a PhD in 2023, in material science from the Federal University of São Carlos, 2019, Sorocaba campus, supervised by Professor Dr. Wagner Botaro. She did a sandwich doctorate at Aalto University, Finland, under the guidance of Professor Dr. Mikhail Balakshin from September 2021 to April 2022 in the Lignin chemistry group. She is currently a postdoctoral researcher at the Institute of Science and Technology of Universidad Estadual Paulista under the supervision of Professor Dr. Leonardo Fracheto. So thank you very much, Jessica, for being with us this afternoon.
Thank you. Can I share my screen?
Yes, you can.
You can see?
Yes.
Yes. Yeah. So good afternoon, everyone. My name is Jessica Rodrigues. Initially, I would like to thank you, everyone here, and thank you, Anna, for the opportunity to present my work to you, for everybody. So I'm going to talk a little about the course of my academic life and focus mainly in the use of lignin, how Anna said. Today, I will specifically focus on lignin and its importance for a sustainable future. The topic of my presentation will be selection of the kraft lignin fraction is to prepare correlation. And as you know, I'm a Brazilian and I live in a country town in the state of São Paulo, called Sorocaba. My city is regarded as an industrial center in the interior of the state of São Paulo, with an estimated population of the 700,000 inhabitants. So it's a big city. Just a little about my scientific career, how Anna said. I have a degree in chemical engineering from the University of Sorocaba, and I did my master and PhD in material science from Federal University of São Carlos, and I did part of my PhD in finance at Alto University. And I'm currently postdoc fellow in environmental science at São Paulo State University. And just a resume about my academic education. So before entering into your main topic, it's important to raise the basic concepts for step development. So what is this definition and concept about the sustainable development? And here I put definition. And sustainable is defined as the ability to conscious use of natural resources without compromising the well-being of the future generation. Its main objectives is to find to balance between economic development and environmental preservation. So in this way, it's important to talk about the sustainable development goals, such as no poverty, zero hunger, good health and well-being, quality education, and others. Several of these SDGs are specifically linked to scientific advances, but require the contribution of science and technology for this. And there are several materials using sustainable technology from natural and renewable sources, such as starch, lignin, cellulose, plant extractives, among others. However, today your focus will be on lignin. And I really like talking about the lignin history, as many people think that its importance was given overnight. Obviously, I will speak in a extremely summarized way, but it's interesting to know a little about the history. Just start with the Anselm Pine. This guy discovered that treatment used with nitric acid and alkaline solution produce a large insoluble reduce we call it cellulose and dissolve scale. You don't nominate this dissolved scale. So in 1857, Schuster later definition this volume material as lignin, a term previously used by Candol, named lignin from lignum, the Latin word from wood. And the guy more important for lignin, I think, Clayson. I think everybody listen just a little. I think about the Clayson. Between 1897 and 1940, Clayson changed chemical structure of lignin. He proposed the lignin was a structure linked to conifer alcohol based on elementary analysis. Macromolecular structure. Sorry. Clayson suggested too. Analytical determination of case lignin. Its insoluble residue remain after treatment used. Tissue with 17% of sulfuric acid to dissolve carbohydrates. Over the years, it was defined as coniferyl alcohol type units joined by ether bonds, and more specific, phenylpropane units with three-dimensional bonds. One of the most consolidated models was proposed by NIMS. He consisting of 25 structure units with oxidative complex of a mixture of the synaptic alcohol, coniferyl alcohol, perchloric alcohol. Sorry. He have a little things about lignin is the second most important lignocellulose biomass, responsible for reforce, impermeability, resistance to microbiome and mechanical attacks, large charge of the phenolic aromatic polymers, amorphous phenylpropanoid structure composed of C9 phenylpropane, formed from the hydrogenate polymerization of three precursor, ICA4. The relative proportion of this precursor depends on the space, location, and source. And difference in the content of the primary precursor are considered to be one of the factors contribute to the great structure heterogeneity and abundance in both agricultural rust and black liquor from the pulp and the paper industry. The main benefits of using lignin can be described as renewable material from natural source, byproducts of the pulp and paper industry, tree production removes CO2 from the atmosphere instead of emitting it, potential to replace fossil-based materials, I think is the more important focus here, and significant increase in the lignin market size for lignin and related products was increased. It was $715 million in 2018, and it's expected to reach to $1,400 million by the end of the 2025. It's a big high increase. And main application and agriculture, it was animal feed additive, fertilizer and soil improvement, and the crop protection. So what is the current challenge? The current challenge is to obtain homogeneous and less complex fractions. And to obtain industrial scale process, for example, the molecular units of lignin must be the same. Equal molecular generate products with the same properties, that is, reproducibility is necessary. To do this, it's important to isolate of active phenolic units. And the solution I'm looking for is the lignin fractionation. I work with this in the last years from my work. What is this? I take the lignin macromolecules and do fractionation, and I can have the different fractions. Here just an example, but here, for example, this guy, it's a part fractionation, the lignin macromolecule in 5 fractions. So you can have different prepares. There are three main methods of lignin fractionation. The first here, it's a fractionation by acid precipitation, where lignin is solubilizated in an alkaline medium and precipitate with acid, where the soluble fraction is separate from the insoluble fraction. Here, we do the separation. You have in this example two fractions. Three in truth because have the initial fraction. And here just an example two, solvent fractionation, where lignin is separated into a soluble and insoluble fraction in a given solvent. Have a lot of solvent study for the acetone, ethyl acetate, have a lot of solvents used in this case. And here it's the same idea, where you put a solvent and a fraction soluble in this solvent is precipitate and you separate. And the last fractionated by filtration, where particles were separated here according to the law cut of the membrane. And here just you do one solution and pass in this low cut of membrane, and high cut you do different cuts of membrane. Here we can see the main advantages and disadvantages of each method. And for example, organic solvents is simple preparation, efficient fractionation, homogeneous fractions with different molar mass, solvent recovery, but have disadvantages, use of the toxic solvents and the high cost of the solvents. And transportation, for example, continued operation and the low energy consumption, versatility in treat different lignin, efficient separation of lignin fraction by molar mass, but high capital cost of membranes and the potential and durability. And the last one, precipitation by variation acid gradients, simplicity in reproduction, energy efficient, but depends of the charge and the structure methods, colloid and precipitation problems, and the low quality due to impurities and the high percentage of the lignin hybridized complex. Here published a paper in 2021 that could be extremely interesting for those who have been working with lignin fractionation. In this paper, you asking one question: can lignin fractions be separated in a true industrial process? And in this review, you're looking for a way to do this fractionation and think about cost, heterogeneity, homogeneity, and you think about this in this paper. So here, catalyzation methods. The structural catalyzation of lignin is extremely important. Based on the catalyzation, it's possible to say which will be the best application of the lignin study. The molar mass distribution must be determined by GPC or geoformation chromatography. And there are several analyses for the chemical structure, such as ultraviolet visible spectroscopy, FTIR, Raman spectroscopy, NMR, and CSPS. If I could say which is the most important, I would definitely say the NMR. However, the other analyses are complementary, so putting some of them together is very important. So you have two thermal properties like TG, TGA, and DSC, and the mechanical properties are currently being analyzed by GMTA. Now I'm going to talk a little about some research I carried out on the correlation between the structural property and the lignin. Say about this, it's a little difficult because it's a big topic for discussion, but I try to summarize this. So here, in this paper, the main objective was to categorization different lignin fraction to correlate with the extra-true prepared correlation and which correlate with structure would be best to replace phenol of fossil origin with lignin and phenol resin. Initially, we separate the kraft lignin into fractions, the soluble and insoluble fraction in ethyl acetate. This solvent was chosen because it solubles low molar mass fraction with high concentration of the phenolic groups. The effect of the fractionation on the structure of the kraft lignin was observed by GPC and FTIR. And thought GPC, we can see that the fraction were separated into intervals of the high and the low molar mass. You can see here, the black is the KL, the kraft lignin, and which the one, the less molar mass. Being the fraction soluble in solvent, the pink is soluble and green is insoluble fraction. As we expected, the soluble fraction was directly linked to the extensive amount of the lignin monomer units with the free phenolic here, free phenolic OH released during the rupture of the ether bonds in the kraft pulping process. The more ether bonds are broken, the greater the presence of the phenolic units, and therefore, the greater the width of this fraction. And here, by FTIR, it was possible to magnetize when increasing the intensity of the phenolic and aliphatic flow for the soluble fraction, demonstrating the OH groups were present in great quantities in this fraction. In 1705, it's possible to see the elongation of the conjugate ester bond, which contributes to the bind of the phenolic groups to lignin. And content of the phenolic hydroxyl group was analyzed by UV visible and NMR, where by UV visible it was possible to see the scatterization peaks of the non-conjugate phenolic structures, aromatic rings, and conjugate phenolic structure. The intensity for soluble fraction, in this case, it's the higher for soluble in ethyl acetate. And for complement this analysis, it's using NMR. Thought this categorization, it was possible to prove that phenolic OH structure here, phenolic, remain solid in the fraction soluble in ethyl state. Here you can see the high percentage for lignin fraction soluble. And for this, the last molar mass of the large fraction was the amount of the phenolic, OH phenolic. Thermal stability of the fraction, KL, was analyzed by TGA, where the higher molar mass fraction showed greater thermal stability, which was expected. So here, higher thermal stability correlation with the higher molar mass. This happened, it was expected, since the higher molar mass fraction need thermal energy to break the alpha ether and or beta O4 bonds present in its structure. And as the objective was to manufacture phenolic resin, the surface were tested and it was possible to observe that hydrophobicity increased with the increase in phenolic hydroxyl group. Here you can see you did to replace first stage where you use 25 and 50% of each fraction. So here, kraft lignin 25 and 50, soluble fraction 25 and 15, and insoluble 25 and 50. The different, you can see the better homogeneity of the LPF resin produced from FL soluble 25 phenol replace results in a better adhesion properties. Here you can see the soluble fraction have similar properties from control after statistical analysis. And on the other hand, the soluble fraction was able to successfully directly replace 15% of the commercial PF resin, showing a performance similar to the commercial PF control and significantly superior to insoluble and kraft lignin in unfractionated. Here, the same fraction used in this work were used in this paper. So here is the same fraction, soluble, insoluble fraction in thioacetate. You use in this case to produce carbon forms, and the structural performance was evaluated. So it was possible to observe in this work. Then when a specific fraction of lignin are used, better final properties can be achieved. It was possible to produce a quantity porous materials that was applied to an electrochemical sensor. Here we have one types of analysis when we can see the improvement of the solubility parameters of the soluble fraction together with a specific post-fractionation chemical characterization, resulting in higher carbon yields, amorphoporous structure with a higher degree of graphitonization, increased surface area, porosity, and average pore volume. It was possible to observe that inorganic results here with others analyzed to observe the inorganic results were retained in the insoluble fraction, leaving the carbon fragility and with the cracks. So when you use different fraction, you produce different carbon forms. And here you can see a difference between, for example, control and soluble. You can see it's similar in this case for application in electrochemical sensor. And here we propose another structural performance correlation. However, for a different application, lignin is well known for its antioxidant properties, and these were tested in this paper. In this work, we studied thermoplastic starch films with different lignin fashion and observed the behavior regarding photooxidate degradation. It was possible to observe that when a specific fraction were used, it was possible to produce plastic that was more resistant to sunlight, and it could be used in automotive tools too. Using a scanning electron microscopy, it was possible to observe the starch films added with different fraction exposed to 0 and 432 hours of the UVC light. And here it's a control, TPS, just a thermoplastic starch. And here, thermoplastic starch with the Kl soluble and insoluble. Here you can see for soluble don't have cracks. The higher percentage in the soluble fraction, the phenolic OH content, made this fraction resistant to UVC radiation greater This factor was attributed to the great amount of the phenolic OSU units. And you see this result in NMR. And for conclusion, after these works, when selection fraction of lignin are used correctly, the final performance of the development products is infinitely greater. So because of this, you need to continue study in this area, because the correlation is really important. Think about this fraction work in that fraction work in the other case. It's important for a suitable future. So my acknowledgement is from my universities, UNESP, UFSCar, Alto University. It's so to thank you for UNA, University Nacional Costa Rica, for the opportunity for talk a little about my work. It's a little time for say a lot of things, but I try to do this. I want to thank the FAPESP and CAPS for grants. And thank you for your attention. And if you need something, if you want to talk with me about these topics, contact me with my email or LinkedIn, what you prefer.
Thank you very much, Jessica, for the presentation. It was quite interesting to see all the work you have done in a rush. But thank you so much for sharing that knowledge with us. Now we will have some time for some questions. So I don't know if someone in the audience has some questions for Jessica. I have no questions in the chat, I think.
No, there are no questions in the chat. However, if someone wants to ask a question directly, you can raise your hand and I will allow the microphone to be turned on. If it's okay, maybe I can start.
Yeah, okay, go ahead.
Yeah. Thank you, Anna. Jessica, thank you for such a wonderful and interesting talk. So I'm an analytical chemist, and in my case, we always want to have like a standard method for the characterization of any property. And based on your studies, there's actually several different methods that give us several different pieces of information. So what would be your recommendation in order, like the place to start at least? Would you say that one of the methods is more versatile or gives more profound information or deeper information than the other, or do you recommend running all of them?
Love, then it's difficult. In Brazil, it's difficult. So you choose. In my case, I choose NMR. NMR, it's really important. You can see the OH phenolic groups, OH different groups, aliphatic groups. And when you see the OH groups, you can have a way, for example, I have higher OH groups in this fraction. This fraction can work for photooxidation, for example. This work have more proprietary for higher yield, carbon yield. You can choose the fraction you work with. I think NMR is the more important of sure.
Yeah, that makes total sense. Thank you, Jessica.
Welcome.
We have Oscar.
Yes, thank you, Jessica, for a nice talk. Yeah, I was wondering about the different fractions you get of by different method, by the solvent method, and the other one by ultracentrifugation. Have you ever seen some difference in particle size of the lignin that you are extracting there? How is the polydispersity of these particles?
The polys I have here in my paper, here don't have time for show, but the polydispersity change with the soluble and insoluble. Insoluble fraction have a higher polydispersion because in this fraction have a lot of the inorganic compounds. So in this fraction, not a good fraction, you can say in this way, but soluble fraction, yes, because inorganic compounds is not soluble in ethyl state. So in this case, you separate this fraction. So the polydispersity for soluble, it's close to 1, and for insoluble, close to 2.5, something 3. It's something like this.
Okay. Thank you.
Welcome.
And what about the yield of every part?
The yield is the higher from soluble because the process, the kraft lignin, they broken the bonds alpha ether, so have a lot of the OH phenolic groups. So in this case, for soluble fractions.
Thank you.
I have a question.
Okay.
Okay. I'm sorry, maybe you mentioned it and I didn't pay attention. The source of the lignin you're using right now?
Kraft lignin.
Kraft, but let's say it's from a tree or from an agricultural waste?
It's an industry from São Paulo here, Suzano. Maybe you listen about. It's an important company here, and we work with the lignin residue from the industry and paper, pulp and paper industry.
Okay, great. Have you ever worked with any other sources of lignin?
I'm working with the organosulf lignin, but the yield is so less, so I don't work more. I work in my master degree, so after my master degree, just work with the kraft lignin.
Okay, thank you.
Welcome.
Luis?
Hello, thank you for your talk. I just have a a quick question. I hope you didn't mention it, because if you did, that means that I didn't pay attention. When you fraction the lignin, the soluble and insoluble part are characterized. I mean, chemically, what are the differences between the insoluble part of the lignin and the soluble part?
The most important difference, structurally different, is the content of each groups in this lignin. How I work with phenolic resin, I focus in OH groups. So I did UV visible. I see the intensity of this group, and for complementary, I did the NMR. And in NMR, we can see the different OH groups in each fraction.
So basically, what you are saying is that the soluble fraction is richer in OH group, in hydroxy groups, than the insoluble fraction.
Exactly.
And besides that, do you know which kind of like other chemical compounds are in these two fractions, or you just are interested in the OH groups, because that's the one, like that's the kind of scaffold that can help you to develop all these materials?
How replace phenol from fossil source? I focus just in hydroxyl groups, But for other application in True, you need looking for other groups for see the difference between this fraction.
Awesome. Thank you very much.
Welcome.
Any other questions? I still don't see any questions in the chat or the Q&A.
I would like to ask maybe the last question from my side. Maybe it's related of the composites you did with mixture of lignin and starch. So you create some films, and I would like to ask you how is the hydrophilicity or hydrophilicity of that films? How is the behavior when you have water in the medium?
I talk about this here. Okay, these films.
Yeah.
The other here, yeah.
Yes.
We correlation the hydrophobicity with the percentage of the start again photooxidate degradation you see and after year. So you see the bands and I remember 75 wave number, and you see these bands in different hours of this pulse of the UV light. So after this, you compare it with the contact angle. So you can see for soluble, we have the more hydrophobicity, I think, for soluble, yeah, hydrophobicity, because insoluble have more OH groups. So in this case, it's more hydrophobicity.
Okay. Okay. Thank you.
Welcome.
Any other questions? If not, I think we can say thank you to Jessica for the talk and answering the questions. And I think we will see you tomorrow to the next talk. Thank you very much for joining us today. Thank you.
Thank you.
Bye.
Bye-bye.